So let's begin our study of proofwriting. So chapter 4 is entirely dedicated to proofwriting. So we're going to cover sections 4.1, 4.2, 4.3, 4, 5, and then we're going to skip 4.6 on floor and ceiling functions, and then we're going to cover 4.7 and a little bit of 4.8. So we're going to start with direct proofs, and then we're going to learn after section 4.6, we're going to learn about indirect proof. So truly the theme of this entire chapter is trying to determine whether or not a given statement is true or false. So we're going to focus solely on problems here that are going to include even and odd natures of integers. We're going to be looking at rational numbers, and we're going to be looking at real numbers. And as I put in the notes, one of the best ways to think of a mathematical proof is as a carefully reasoned argument to convince a skeptical listener that a given statement is true. So essentially, what I'm looking for is I would like to see if your proof can be read by your average high schooler and if they can follow it. So that's kind of what I'm looking for, all right? So oftentimes what the easiest way is to remember is when you add a line, say, why is that? You add something to your proof. Why is that? If you don't answer the why you included it, then perhaps you need to add something to your proof. So in practice, once you've done this quite a while, we start to omit some of that reasoning just as assumptions. But for this class, it's better for you to err on the side of providing too much information than not enough. But we will allow you some wiggle room here, especially in terms of what can we assume that the reader of our proof knows. And I'll leave the rest of those notes for you to read. It's just a general introduction to proofwriting. So the assumptions that we can make in this class are as follows. Appendix A of the textbook. So what is in Appendix A? That's all your basic algebra properties. That's what's in there. So we're going to assume that both you and the reader are familiar with the laws of basic algebra, and we're also going to say that we can use the 3 rules of equality. A equals A. If B equals A, then A equals B, right? If 2 equals 2, then 2 equals 2. So if A equals B and B equals C, then A equals C. So what we have here are properties that are reflexive, symmetric, and transitive. You'll hear those terms again in a few weeks when we get close to the end of the semester, when we start talking about equivalence relations. So we're also going to use the principle of substitution. So for any object, A and B, if A equals B, then we may substitute the letter B anywhere where we have the letter A, and vice versa. And the last assumption we're going to make is that there is no integer between 0 and 1, and the set of integers is closed under addition, subtraction, and multiplication. This is probably a new term to all of you, or at least most of you, but closed is something that's going to come up over and over again. We're going to talk about closure of different types of numbers. You can think of it in terms of coding as the accepted operations for a data type. So if we're talking integers, we know here that if I add 2 integers, I subtract 2 integers, or I multiply 2 integers, my result is still going to be the data type integer. Same thing is going to hold true for rational numbers. Rational numbers are fractions. We know that they are going to be closed under addition, subtraction, and multiplication as well, because addition of 2 fractions, still a fraction. Multiplication of 2 fractions, still a fraction. Difference of 2 fractions, still a fraction. So we're going to be using this language in our proofs. So we're going to be saying, because integers are closed under addition, subtraction, and multiplication. Because rational numbers are closed under addition, subtraction, and multiplication. Those sorts of things. So you're going to be required to use that kind of language in your proofs to show that you understand this property. So where do we even begin with proof writing? And I labeled this one sort of jokingly, I already know what that means. Because where are we starting? We're starting with terms that everybody knows, right? Everyone knows what it means, but can you define it? For example, even. Can you define what an even number is? So a lot of people will tell me, well, it's a number that's divisible by 2. And while that's great, we just talked about closure of integers and it didn't include division. So let's say the same thing, but in a slightly different way. What if we say that an integer n is even if and only if n is equal to 2 times some integer? Is that saying the same thing as it's a number that's divisible by 2? Well, now we're saying pretty much the same thing, because we're saying instead that it is a multiple of 2, which if you think about it is saying exactly the same thing. And wrapping your head around a way to rephrase division is going to be a good skill to have by the time we hit section 4.4. So what does this look like as a formal definition? Our formal definition here is going to say, for all n in Z, n is even, and remember, if and only if is that biconditional arrow, there exists some k in Z such that n equals 2k. This is our important definition here for even. So can you think of a way to describe odd? And no, you can't just say it's not even. You could lead into that idea of consecutive from before, but remember what we did to show that it was consecutive. We took a number and added 1. So if we took an even integer and added 1, we should come up with an odd integer. So we're going to say an integer is odd if and only if, oops, I forgot the n. So an integer n is odd if and only if n equals twice some integer or 2 times some integer plus 1. So as an official definition, we end up with, for all n in Z, our formal definition says n is odd if and only if there exists some k in Z, meaning it's an integer, such that n equals 2k plus 1. Again, this is one of our important formal definitions. So far we've described even numbers and odd numbers. Let's talk about a prime number. I asked you at one point what you thought a prime number was and if you thought 1 was prime, and a lot of you said yes. which we normally would because that's what we were taught when we were young. However, that is not actually the definition of a prime number. So a prime number, if you remember, is a number that is divisible only by itself and 1. So an integer n is prime if and only if. Now this one's going to have kind of a weird definition, but it just means that it's divisible by itself and 1. So if and only if n is greater than 1, so right there, our definition removed 1 as a prime number. So if and only if n is greater than 1, and for all r and s in the set of integers, positive integers, I should definitely keep that in there. If n equals r times s, then r equals n or s equals n, meaning that n has to be one of the two factors. So the formal definition for this one isn't really all that different. We would just say that for all n and z, n is prime if and only if n is greater than 1, and for all r and s in the set of positive integers, if n equals rs, then r equals n and s equals 1, or s equals n and r equals 1. So another formal definition of prime. And our last formal definition here is going to be a composite number. You may not have known this is what they were called. These are our numbers that have other factors. So if we have prime numbers, we have to have numbers that aren't prime. So these are the not prime numbers. So an integer n is composite if and only if n is greater than 1 and there exists some r and s in the set of positive integers such that n equals rs and r is greater than 1 and s is greater than n. So what that means is that one of our factors here is bigger than 1 and the other one is less than n. Oh, I think I wrote, let me erase that. I wrote greater. I meant to write less. So our official definition here, our formal would say, for all n in z, n is composite if and only if n is greater than 1 and there exists some r and s in the set of positive integers such that n equals rs and r is greater than 1 and s is less than n. That's our last formal definition for this section. So moving forward, we're actually going to use all of these definitions to try out some different values. And that's what we're going to do on the rest of this page. So let's start with asking, is 0 even? Well, we know that a number is even, an integer is even, if it's a multiple of 2. Can 0 equal 2 times another integer? And the answer is yeah, absolutely yes, because 0 can equal 2 times 0, where 0 itself is in Z, right? And 0 times 2 is in Z. So here, we're just saying where 0 is an integer. And this would be, our reasoning would be by the definition of even. Can we show that 1 is prime or is not? The answer is yeah, we can. So is 1 prime? The answer is no, because prime numbers, by definition, are greater than 1. And that is by the definition of prime. Okay, not so bad. Let's try a couple more. Is negative 301 odd? Well, your first inclination is like, well, yeah, it's not even, so it has to be odd. Which is true, but remember, we're applying the definition of even and odd. So we need to show that negative 301 can equal 2 times some number plus 1. And so now your first inclination is going to be negative 150. But what happens when we do 2 times negative 150 and add 1? We get negative 300 plus 1, which is negative 299. That's not going to work. So we're going to have to come up with another option. So we're going to cross that one out. Let's try it again. So let's say negative 301 equals, how about 2 times a negative 151 and add 1. Then we get negative 301 equals negative 302 plus 1, which would give us a negative 301, which is exactly what we wanted. And we know that negative 151 is an integer. So this is by the definition of odd, our reasoning there. So now that we've looked at some different values here for possible even and odd numbers, let's try a couple of other concepts with evens and odds and primes and composites. So if I know that a and b are integers, is 6a squared times b even? So the way you have to think about this is, can I make that value a multiple of 2? Hopefully you said yes, because you can factor out a 2. So we would say yes, because 6a squared b equals 2 times the quantity 3a squared b. And we know this because 3a squared b would be what type of number here? Hopefully you said that 3a squared b is an integer, because integers are closed under, and all we used here was multiplication. That's the way we're going to say it when we start writing our proofs. Integers are closed under multiplication. So 3a squared times b is also going to be an integer. So therefore, 6a squared b equals 2 times an integer, and thus 6a squared b is even. And that's by the definition of even. So you can kind of get a sense now for where we're going with all of these words and what we're going to be doing with all of these applications in our proofs. But before we jump all the way forward, let's just talk a little bit about some prime numbers and some composite numbers. So I asked you here to write the first 6 prime numbers. And remember, 1 is not prime. My next question is 2 prime? Hopefully you said yes. 2 is prime, so is 3. 4 is not, 5 is, not 6. Yes, 7, not 8, not 9, not 10. Oh, but 11 is, not 12, but 13 is. Those are our first 6 prime numbers. So these are numbers that only have divisors that are themselves in 1. They're only multiples of themselves in 1. If we want to write the first 6 composite numbers, remember that's also starting greater than 1, so we're going to find all the numbers that kind of went in between the primes, or the ones we didn't use for part E. So 2, 3, okay, 4 would be in there, 5 is prime, 6 is not, 7 is prime, 8 is not, 9 is not, 10 is not, 11 is prime, so 12 is composite. 1, 2, 3, 4, that's 6. So we could keep going, and if you'll notice, there's this pattern of prime, composite, prime, composite, prime, composite, back to prime, back to composite, back to prime. You put them all together and you have all of the positive integers starting at 2. Of special note, how many of our prime numbers are even? Hopefully you said only 1. Only 1 even prime number, and that is 2. Simply because as soon as you do the next even number, which is 4, now not only does it have multiples of 1 and 4, but also 2 and 2. So any other even number you're going to be able to factor out of 2, so it's no longer prime. So there's only 1 even prime number. So how about this last one on this page? If a and b are integers, is 10a plus 8b plus 1 odd? Well, the question is, can I rewrite this as 2 times an integer plus 1? Well, the plus 1 is already here, so we need to get this to be 2 times an integer. I think we can do that. Just factor out a 2. So we're going to say yes, because 10a plus 8b plus 1 is going to be the same as 2 times, and we'll be left with 5a plus 4b, and then plus 1, right? And we know that 5a plus 4b is an integer because integers are closed under, and here we used addition and multiplication. So thus, we have that 10a plus 8b plus 1 is now equal to 2 times an integer plus 1. So therefore, we would say that 10a plus 8b plus 1 is odd. And that would be by the definition of odd. Before we can begin writing proofs, we need to understand how to write proofs. So we're going to be beginning with direct proofs, which means that we're going to start with a universal conditional statement, and then we're going to use our universal modus ponens argument form to prove that it's true. So the vast majority of mathematical statements to be proven are given in a universal form, particularly in a universal conditional form. And like we saw in section 3.3, when the domain of a universal statement is finite, it is possible to prove the statement via the method of exhaustion. However, when it's an infinite domain, we need another option because we would never stop writing if we tried to use the method of exhaustion to prove a universal statement true for an infinite domain. So knowing what we know about conditional statements, which are our reminder are our if-then statements, and they can only be false if the hypothesis is true and the conclusion is false. So if we are given if P of X then Q of X, we can then show the truth of P of X compels the truth of Q of X. And when we can do that, then we will have proven our universal conditional statement to be true. So this method is via our universal modus ponens. So if you remember back from section 2.3, our modus ponens was if P then Q, P, therefore Q. So it was confirming our hypothesis was true and that our hypothesis was compelling our conclusion to be true. In our universal quantified version of that same argument from section 3.4, we simply add in a domain and we define each of our statements over our domain. So in this case, remember, we would have here in our universal modus ponens, we would end up having universal modus, sorry, I gotta catch up to what I'm saying. In our universal modus ponens, we would then say for all x in our domain, whether our domain is the set of all real numbers, the set of rational numbers, or the set of integers. Those are the three universal sets we will tend to define in our course. So for all x in that domain, if P of x, then Q of x, and we would say then P of x, therefore Q of x. And the nice thing is about doing our quantified versions of the universal modus ponens is that when we then have instead of just one integer, then we can just modify our universal modus ponens to include both integers, or both real numbers, or both rational numbers. And we'll see that when we get to some of our examples on the next page. So how does our method of direct proof work with our universal modus ponens? Well, the first thing we're going to do is express our statement to be proven in the form of for all x in D, our domain, if P of x, then Q of x. So in other words, we're looking at the same first line as our universal modus ponens argument. And step 2 says we're going to start the proof by supposing that x is a particular but arbitrarily chosen element in our domain D for which the hypothesis P of x is true. How this relates to our general form of modus ponens back in section 2.3 is that we're assuming that P is true. In this case, we have an x in our domain and that we're going to assume then that P of x is true. So our statement P is true for that particular but arbitrarily chosen x that's in our domain. So oftentimes we will abbreviate this step. Suppose x is in our domain and P of x. So that's where we're going to start all of our proofs in direct proof. So that's going to carry us all the way through section 4.5. When we switch over to section 4.7, we're going to talk about indirect proof. We're still going to use our universal conditional statements, but we're going to apply them in a more circuitous path. More on that when we get to section 4.7. To finish off our method of direct proof here, though, we're going to say on step 3, we're going to show that our conclusion Q of x is true using definitions, any previously established results which technically we don't really do in this course, but it can be done if you're using this method of proof in another course and you're allowed to pull in the solutions you have for a proof before it or something along those lines. And then the rules for logical inference. In general, your goal is to make sure that you're constantly keeping your reader updated on what is happening in your proof and not leaving them to sit there and make assumptions or constantly be going, but why? I don't understand what happened here. How did you get from point A to point B in your proof? I need you to connect the dots. Those are things that shouldn't be happening when you're just learning to write proofs like we are in this class. In this class, erring on the side of more information than less is better. So we're also going to need some directions for how these proofs should be written in this course. So I'm going to give you this list of directions for writing proofs for universal statements. The first one is to copy the statement of the theorem to be proven onto your paper. So when I'm asking you to do this, I'm asking you to write out the statement as a universal conditional statement here. So you want to label it as, and on your paper you'll put statement or on Canvas, and you will underline it and say this is my statement, and then you will write it as, right? Then you will write it as a universal conditional statement. Why? Because then it's a lot easier to see where our universal modus ponens is being applied if we can see what it is we are allowed to suppose is true and what it is we must show is true if P of X is true. We're going to clearly mark the beginning of our proof with the word proof. And again, just as statement, you'll write it as the word proof and underlined. You won't be including the quotes here. I'm just showing you what it is that you're going to be writing. Number 3 says to make your proof self-contained. You might be asking, what does that mean? Well, it means that you're going to explain the meaning of every variable that you use in the proof within the body of the proof. So, for example, if you're beginning your proof with suppose m and n are any even integers, or let x be a real number such that x is greater than 2. Those would be ways that you would include what types of variables x and m and n are. At some point later in your proof, you can introduce new variables to represent quantities that are known at that point to exist, such as since n is even, n equals 2s for some s in the set of integers. If you are familiar with programming, you can think of this as defining your variables or declaring your variables as you are writing your program. If you try to use a variable in a program that you haven't declared, your program will not run. It won't compile, it won't run, you'll get an error. Number 4 is also vitally important. It's write your proof in complete, grammatically correct sentences. If your reader cannot understand the explanation, then they can't understand the proof. And you're going to be writing sentences. No points are going to be deducted for incorrect placement of commas or using the wrong it's or the wrong there if those words happen to show up in your proof. Generally speaking, if I see a grammatical error, I will fix it and give you some feedback to say, don't forget that you need to make sure this is a complete sentence. Number 5 says keep your reader informed about the status of each statement in your proof. So you should never be making your reader guess what is going on. You should always be stating the assumptions that are being made so that your reader can follow along very, very clearly with what it is you are doing and what your logic is. Number 6 says, and it's kind of along the same idea, right? Give a reason for each assertion in your proof. So much like we said before, state all of your assumptions. Now you also have to give a reason for each assertion in your proof, which should come directly from the hypothesis or theorem that you're using here. It should follow from a definition of one of the terms in the theorem, or be a result obtained earlier within the same proof, or be a mathematical result that has been previously established or is agreed to be assumed, such as the definition of even, such as the definition of odd, right? And some of the mathematical operations we spoke about earlier, equality and those sorts of things. Number 7 may sound a little picky, but it helps with the flow of the proof. And it is to include little words and phrases that make the logic of the statement clear, such as then, thus, so, hence, therefore, consequently, or it follows that. You will find that I use these all the time. My rule is you cannot begin a sentence with math. If you are making a mathematical statement, your sentence should begin with so, then, it follows, consequently, those sorts of small linking words. So I'm going to write it in here. No sentence should begin with math, right? No sentences, there we go, beginning with math. Meaning you don't just say 4x plus 5 is an integer because. We don't start with 4x plus 5. We would say thus 4x plus 5 is an integer because. Number 8 says display equations and inequalities on their own line. This one is very, very important for readability. The ability to read a proof very quickly and easily and have all of the information contained in a very, very organized fashion. We need this idea of putting each equation and each inequality on their own line. So your proofs should look something like, here's the word proof. Here's where I'm starting, here's my word statement. Here's my universal conditional statement. Here's my word proof. Here's me supposing that P of X is true by the definition of, and then I'm giving some information, some more substitution, blah, blah, blah. There's my conclusion, and I'm done. This is the, yes, correct way to do it. What I will not accept as a form of proof writing, and generally most math professors would not like this, is to see you have your statement and you wrote it out as universal conditional and you write the word proof and then you just start writing line after line after line after line, and you include all of your math all across one line and you just write it in the form of a paragraph. We call these paragraph proofs. Paragraph proofs have no place in this class. So we're going to be making sure that all of our proofs are spaced out. Considering we're not going to be actually writing these down on paper, it hurts no one to hit enter after each line of your substitution and your algebra work in a proof. So I won't be accepting paragraph proofs. And you might be wondering why I put these little boxes at the end of each of the proofs. Well, that's step number 9. Back in step number 3, we said, not step number 3, step number 2, we clearly defined where our proof began. Step number 9 says, well, you have to end it. You can't leave your reader guessing if the next words are still part of the proof, if the next bit of information after it is still part of that proof. You need to give them a very clear message that the proof is done. I have proven what I needed to prove. Now I am finished. So we do that, and you've probably seen this in a lot of textbooks where they mark the end of a proof with this box that we have here. So either maybe an empty box or a filled box. You're going to find when I do proofs writing in my videos, and I do them when I teach this class in person, when I do it in person, I end mine with QED. That reason is that I'm terrible at drawing boxes, as you can see from my example of the paragraph proof. I'm terrible at drawing boxes, so I don't like it. I don't like how messy it looks. So I simply end all of my proofs with QED. Yes, I will take off a point on your proofreading, on an exam, on a homework, etc. if you do not end your proof appropriately by putting a box, by putting a QED, something along those lines. And if you are not familiar with how to do so in LaTeX, if you would like to do that on Canvas, the way that you get this little box here is you can, if you go into the advanced editor using the LaTeX, it's just simply /square. And that will put a box at the end of your proof. I think there's other ones. I think there's like black box, maybe the other one. I'd have to look it up again to remember which ones are which. But you can do /square, or you can simply not bother with the equation editor for that last line and just write QED. Since we'll be typing this in, I'm not going to take off any points or get super picky about where the QED is, whether it's on the left or it's on the right. Typically, we will put it to the bottom right of the last line of our proof. I will not be super picky about that. You can put it as the last line after your proof because you're typing it all in Canvas. Now that we've taken the time to go through the painstakingly thorough process of learning the idea behind writing a proof, let's practice writing proofs. So we're going to start with some very basic proofreading. So the first thing we're going to prove is that the sum of any two even integers is also even. So if we think about our domain is going to be the set of all integers, but now we're going to have two integers. So let's think of our statement, how we would write this as a universal conditional. So we would say for all, and we need to name our two integers. We don't currently have any variables that we've used for the integers, so I'm going to choose m and n. So for all m and n in a set of integers, if m and n are even, then their sum, m plus n, is also even. If we want to know how to begin our proof, let's take a moment to step back and think about what our universal modus ponens looks like here. So the first things first, we're going to have for all, and this we'll use m and n again, m and n again. So we'll say for all m and n in the set of integers, if p of mn is true, then q of mn is true. We would then suppose that p of mn is true for some particular but arbitrarily chosen values of m and n that are integers. So we would assume p of mn is true. And we would show then, therefore, it compels q of mn to be true. So what we're going to do is we're going to color code these steps. So I'm going to replace this p of mn with another p of mn that's in red. Let's do that. And then we will write what we're going to suppose p of mn in red when we write our proofs. And then we will finish in blue. So we will replace our q of mn here with a blue q of mn. And when we move into showing that q of mn must be true based on all of the information we got from supposing that p of mn was true, then we will know when we're done. So we said for all m and n in the set of integers, if m and n are even, then m plus n is even. So our proof says then we get to suppose everything up through p of mn is true. In other words, we're going to suppose that p of mn is true for some particular but arbitrarily chosen values of m and n in the set of integers. That sounds like a lot of words that we're going to put into writing. We're going to say suppose, right? Suppose that m and n are integers, right? And we could do it that way. And we could say, and m and n are even. So yes, we could write it out this way, but that seems sort of verbose, and we could actually write it in a much more succinct way by saying, what if we suppose that m and n are even integers? That's probably a more succinct way to say it. So now the goal is to use any definitions or theorems that we can to give us as much information as possible about what we just supposed is true. So we supposed m and n are even integers. Luckily, earlier in the section, we talked about what the definition of even was. So to give our readers the reasoning, we're going to say, by the definition of even, we're going to say that m equals 2a and n equals 2b. Now notice we introduced two new variables, a and b. And again, if you're a coder, you'll remember that if you introduce new variables, you have to declare them. The same thing is true when we're running our proofs. So we introduced a and b, so we need to say this is for some integers a and b. So we'll say for some a and b in a set of integers. So at this point, we have no other definitions that we can apply. So we've thoroughly exhausted what we know about P of Mn. So now we have to go about showing that Q of Mn is true if we assume that P of Mn is true. So we're going to start by saying by substitution, and let's show that what we're trying to substitute. Well, what is that? Well, we're trying to show now that Q of Mn is true. In our statement, we have P of Mn is m and n are even. And Q of Mn would be m plus n is even. So what we're trying to show here is that m plus n is even, based on this definition that we just provided, because we were able to assume that P of Mn is true. So by substitution, and this is the important part, make sure you show first what it is you're substituting into. So we will say m plus n first, and then we will equal, well, m is the same as 2a plus n was given as 2b. So we're trying to show that it's even, which means it's 2 times some integer. So we will say that that equals 2. We'll factor out a 2, and inside our parentheses we're left with a plus b. So now we know that we have 2 times an integer because integers are closed under addition, meaning that sums of integers are also integers. But we need to show this to our reader, so we're going to say, let's let P equal a plus b. Then we know then that P is an integer because integers are closed under addition. Integers, remember, are also closed under subtraction and multiplication. So in this case, we just had an addition of 2 integers, which is then also an integer. So we're going to say let P equal a plus b, and then we want to know, or then we want our reader to know that that means P is an integer because integers are closed under addition. So that is also our way of declaring what P is. We just declared its type as integer based on the fact that we just added 2 other integers. Well, how does this help us? We would say thus, if we continue our m plus n simplification, that means 2 times a plus b becomes 2 times p now, right? So we would have 2p for some integer p, so for some p in a set of all integers. And why would I write it again? Because this is the formal definition of even. So we would say, therefore, by the definition of even, we know then that m plus n is even. And it has been shown, so I write my QED, and again, you can put your either open or filled in box. So this one took us a little longer than typical. The rest of them we'll probably do a little bit quicker because now we have this idea of start with my universal modus, or start with my universal conditional, and then prove that it's true through universal modus ponens. So let's try another one. And that is that we're going to prove that the sum of any two odd integers is even. So we're going to do this one together. And then after part B, I'm going to have you pause and try proof C on your own using the results from A and B. See if you can do it on your own. So we're going to start with our statement for part B. Prove that the sum of any two odd integers is even. So our statement says we need to figure out what the domain is. Well, we have integers. So we know again that we have two integers. So I'm going to use m and n again. So for m and n in the set, for all m and n in the set of integers, if m and n are odd, then we know what? M plus n is, and it's still even. So if you're worried about the truth or falsity of either of these statements, you can in your head consider an example. So for A, we see the sum of any two even integers is even. 2 plus 4 is 6, that's even. So yeah, that's a true statement. How about B? Prove that the sum of any two odd integers is even. Might sound funny on the surface, but if you think 5 plus 3, that's 8. That's even. So yeah, that would work. So you can't use examples to write a proof, but you can use them to convince yourself that the statement is true. Let's start our proof. We have for all m and n in the set of integers, if m and n are odd, then m plus n is even. So we can suppose m and n are odd integers. And now we set about describing these odd integers using a definition. Luckily, we saw one earlier. By the definition of odd, we then know that m is equal to 2a plus 1 and n is equal to 2b plus 1 for some a and b that are also integers. So then we move into the process of showing that q of mn is true. We're going to do this through substitution. So by substitution, now we're substituting back into m plus n again. M plus n is what we're substituting into, so we'll show that first. And it's equal to, well, by equality, we know that that's 2a plus 1 plus 2b plus 1. So we end up with 2a plus 2b plus 2. And we can factor out a 2, and we're left with a plus b plus 1. If we let p equal a plus b plus 1, we can say then that p is an integer because integers are closed under addition here. We didn't have any subtraction or multiplication yet. We'll get to those. If we continue our simplification, then we would say thus, because we can't start a sentence with math, m plus n equals 2p for some p in the set of integers. Therefore, by the definition of even, which is 2 times some integer, which we just showed, m plus n is even. And it has been shown. So we can write our QED. What I'd like for you to do for part C now is to pause the video and try part C on your own. Part C says, prove that the sum of an even integer and an odd integer is odd. See if you can do that. I hope that you tried this on your own before coming back. If not, that's okay. We will still walk through it together, but you'll get the most benefit from trying some of these problems on your own before seeing the solution. So let's write our statement. Prove that the sum of an even and an odd integer is odd. So we're going to say for all m and n in a set of integers, if m is even and n is odd, then m plus n is odd. And now we need to set about writing our proof. And by the very nature of even and odd, it really doesn't matter whether you choose m to be even or odd or n to be the even or odd. As long as you have one variable being even and one being odd, you have this one well in hand. So our proof says then that we can suppose that m is an even integer and n is an odd integer. And since we can suppose those two things, we can now use their definitions. By the definition of even, we can say m equals 2a for some a in the set of integers. We can also say by the definition of odd, we know that n is 2b plus 1 for some b in the set of integers. Now that we've exhausted all of our definitions, we can move into showing that Q of Mn is true. So we would say by substitution, we've got the hang of this now, m plus n equals, m is now 2a plus n, which is 2b plus 1. So remember, what it is we're trying to show is that m plus n is odd, which means we should get 2 times an integer plus 1. So we will factor out a 2 from just the a and the b. So we will get 2 times the quantity a plus b and leave the plus 1 at the end. Because now we have 2 times an integer plus 1, which is the definition of odd. So we will let p equal a plus b. Then we know that p is an integer because integers are closed under, and again, addition. So thus, m plus n, if we carry on our simplification, is now 2p plus 1 for some p in the set of all integers. So therefore, by the definition of odd, which is 2 times an integer plus 1, m plus n is odd. And it has been shown. And again, you can use an empty or a filled square if you would like to do that instead. We're going to wrap up sections 4.1 and 4.2 with some common mistakes and an example on finding an error in someone else's proof. So some common mistakes that happen, and I have seen all of these happen. So The first one is arguing from examples. Remember how I referenced this earlier? You cannot prove an infinite statement through method of exhaustion. By the very nature of infinity, it never ends. So you would never stop having to prove, never stop writing examples. There is not a way to show that a statement is true for an infinite domain by using the method of exhaustion. So you cannot argue from examples. Just plugging in some numbers is not proof. That's a particular example. You would have to do it for every single possible value, and those values are infinite. Number 2 is using the same letter to mean two different things. Notice when we were doing our proofs for 2 evens and 2 odds, we did an M and an N. They were separate. But so also was their definition. One M, well, the M would be equal to 2A, and N would be equal to 2B. We wouldn't want to make it M equals 2A and N equals 2A, because then we're saying that M and N are the same even integer, which defeats the purpose of proving that the statement is true for all even integers. It wouldn't be true. That would be just true for the same M and N. And that's what we say in number 2. We don't want to suppose that by definition we can use the same letter over and over and over again. So for this example, instead, we should probably say if M is 2K plus 1, let N be maybe 2Q plus 1, 2P plus 1, 2A plus 1. Choose a different variable. Number 3 and number 4 go together a little bit. That's jumping to a conclusion. So jumping to a conclusion within the body of your proof is skipping a bunch of steps and assuming the reader will just figure it out on their own. That violates our rules for proofwriting. Not acceptable. And number 4 is assuming what is to be proven. That's our converse error. That's assuming that Q of Mn is true or Q of X is true, and then trying to compel the hypothesis to be true just because you assumed the conclusion was true. Number 5 kind of goes along the same lines as number 3, and that's confusion between what is known and what is still to be shown. So read through what you're writing to make sure that you haven't skipped over some information that you thought you'd already shown that you have not. 6, I don't see this one as often. It's very rarely 6 and 7 are a problem. Use of any when the correct word is some, and that's our difference between our universal and our existential quantifiers. And number 7, the misuse of the word if. The word if has no place in your proof. The way we are writing proofs, you will not use the word if within the body of your proof. The last time you will write the word if is when we write the statement as a universal condition. So let's look at our last example here, and we're going to try to find a mistake in the following proof. What the student is trying to prove is that the theorem, if n is any even integer than -1 to the power of n is equal to 1, is true. So our proof is we get to suppose that P of n is true. So we're going to suppose that n is any even integer. So far, so good. Okay, we can check that box off. Okay. By the definition of even, n equals 2a for some integer a. Okay, that sounds fair. The student wrote out by the definition of even, so they gave their reasoning. They said n equals 2a for some integer a. Fine. Then they said, okay, now let's move into proving that q of n is true. So we're going to use by substitution. Perfect. Still updating the reader. You're so far, so good. We said -1 to the n equals, and that's good. And we substituted in n is 2a. So far, so good. Then we said that equals -1 to the a, quantity squared, and we said that equals -1. I believe I have I had a box on there that I think disappeared. There was a box there to show that it was done. So assume that that is there as well. I think when I downloaded it, it sort of disappeared. So where did our student make the mistake? We want to pause and see if you can figure it out. The mistake was in this line. Try to figure out what that mistake is. In this case, they said -1 to the a, and then squaring it is always 1. Well, what they don't explore then is -1 to the a if a is even, and -1 to the a if a is odd. So there are two different cases that this would need to be split into. So they skipped some information. So they skipped some steps, right? So they jumped from, right? They jumped from -1 to the 2a, or sorry, to the a to the 2 to just equaling 1. So that's, I mean, it's true that the square of any non-zero real number is positive. It doesn't follow that -1 to the a is always going to be 1. And they didn't show then that -1 to the a is, when it's squared, is going to be 1 for both even and odd. So they didn't show that -1 to the a squared is positive 1 for both even a and odd a. Here's the thing, we have a workaround. We can get around this. Let's see if we can figure it out. So we could say, okay, I'll write my statement. And I know they didn't really have a statement, they just did the theorem. Well, we'll write out our statement and we'll just leave it as the theorem. So let's see here, theorem, and we'll say if n is any even integer, n is any even integer, then -1 to the n equals 1. So we'll leave it the same. It's not a universal conditional, but that's okay. It's just an example. And then we will write our proof. We're going to follow the same thing. Suppose n is any even integer. And remember from chapter 3, you could also just say an even integer, because remember that's an implicit quantification for any, our universal quantifier. So we're going to suppose n is any even integer. Then by the definition of even, n equals 2a for some a in the set of integers. So I realize the student wrote it slightly different than that, but it's the same idea. Then we move into our substitution. By substitution, -1 to the n is now going to be -1 to the 2a. But the way we can get around having to show these cases is that we can say this is -1, and instead of splitting up the exponents to be a and then 2, flip them around. Do it 2 and then a, because -1 squared is always 1 to the a, because it's always -1, or -1 squared is always 1, and 1 to any power is 1. So, and in this case, this is a computational one, so we don't have anything else to write. So we are done.